Galileo Galilei. I wish you become a scientist like him. Hello, this is Dr. Bin Song at Washington College. Among all modern scientists who have helped to initiate and somewhat complete the modern scientific revolution since the ingenious work of Copernicus, I like Galileo the most. He wrote his groundbreaking scientific works in the form of Socratic dialogue and using a fairly accessible vernacular language, namely Italian, in his time, which was to imitate Plato's prototypical genre of philosophical writing. While presenting his trailblazing new science, Galileo also seriously thought about so many topics significant for the development of philosophy in general, among which God, humans, and nature are by no means trivial mentions. Most importantly, compared with Descartes and other continental philosophers in the early modern period, Galileo was down to earth and always tried to embed his rigorous reasoning within experiments, observations, and hence made sure that such reasoning does not fly too high away from humans' common sense. If I have to express what I expect science majors in the college to become after they graduate, I wish they would be like Galileo, a gentle, well-rounded, and a wise scientific soul. Seen from the perspective of Galileo's entire career, he had to accomplish 3 tasks in order to continue the scientific revolution started by Copernicus. He had to deal with 2 authorities which swayed a great power in the scholarly world of Galileo's time: the authority of the Bible and the authority of Aristotle. After this, he surely needed to present his new scientific discovery in the most accessible and professional way. His way to address the authority of the Bible on scientific matters is best represented by one letter to Castelli, which he wrote in 1613. He views that the Bible and the new science take charge of different things. Regarding salvation and other articles of faith, the Bible has its absolute authority. However, since God the Creator endows human beings with sense and reason, for Galileo, there is no reason not to use them, and therefore the new science has its irreplaceable authority regarding the study of nature. If verses in the Bible seem to contradict what the new science discovers, we should seek wise interpretations of these verses so as to make the biblical truth compatible with the scientific ones. In this letter, the refutation of Galileo against the scholars' use of the Joshua 10 to discredit Copernicus is fun to read, since according to Galileo, Copernicus' heliocentric astronomy makes more sense of the biblical verse, which implies God's command to stop the movement of the sun. And hence this is also a great example of how a scientist can provide a wise interpretation of the Bible so as to square the authority of new science with the one of religious establishment. The second authority Galileo needs to address is Aristotle, who, as we discussed before, held an absolute authority among scholastic scholars regarding the study of nature. In the dialogue on the 2 chief world systems, Galileo discusses the authority of Aristotle in this way: only blind people need a guide when they walk in flat and open region. However, for anyone, quote, who has eyes in his head and in his mind should use them as guide, quote. In other words, sense and reason are the genuine guide for humans to pursue science. Even if Aristotle was still alive in Galileo's time, Galileo believed that Aristotle would admit many of his mistakes in his original scientific writings in light of new evidences and demonstrations. Therefore, Galileo concludes that it is due to the lack of courage that scholars in his time stubbornly held onto the old authority of Aristotle in order to refuse new approaches of the study of nature. Through Galileo's writings on the two authorities, we find origins of many significant ideas of modern philosophy, such as John Locke's separation of church and state, and Kant's definition of enlightenment as the courageous use of human reason in public. I once explained that the reason for us to study modern scientific revolution is to find origins of these ideas we initially discussed in the first section of the course on the Enlightenment. I hope you understand why this is so now. Finally, the most important part of Galileo's work is surely to present his new discoveries using the new scientific methodology. In this regard, I select an excerpt of Galileo's dialogues concerning two new sciences for your reading, and from here you can discern such a classical use of scientific method that scientists have consistently employed it since the time of Galileo, and as a consequence, such an application also caused so many profound transformations in human society. The thinking procedure of Galileo's work, which he called a new science of motion, can be summarized as follows. Firstly, to define the overall nature of the work, Galileo says that why such a science is new in comparison to old ones is because it cares about the exact mathematical measures and proportions that an accelerated motion indicates. Secondly, to propose a new hypothesis about an unknown matter, namely the uniformly accelerated motion, from the knowledge scientists already have, namely the uniform motion. In other words, since we already know in the case of the uniform motion that space traveled by an object is proportionate to time, we can hypothesize in the uniformly accelerated motion that the increase of velocity of such an object is proportionate to time as well. As indicated in other scientific endeavors, proposing new hypotheses on unknown matters according to known ones involve genuine creativity of human thought on the basis of lots of guesses and trials. In this regard, there's really no strict method to follow. Although we can discern a pattern of human thought to say a new hypothesis is proposed according to what is already known. However, this is just a pattern of thought, and how this pattern is manifested in varying cases really depends upon unpredictable human creativities, among which Galileo's one is by no means negligible. Thirdly, to resolve conceptual difficulties implied by the hypothesis. In this case, the difficulty is about how to envision the infinitesimal increase of speed at the initial moment of a uniformly accelerated motion. Fourthly, to disregard distracting questions which are normally more complex than the ones a newly proposed hypothesis is intended to address. So, Galileo argued with his friends that before we study the cause of free-falling object, we needed to describe the mathematical traits of its uniformly accelerated motion at first. This also speaks to a constant nature of scientific reasoning. We need to put things in order so that before tackling more difficult questions, let's tackle easier ones at first. Fifthly, to refute competitive hypotheses on the same matter. In this case, the alternative hypothesis that the increase of speed of a uniformly accelerated motion is proportionate to space rather than to time would lead to absurd consequences, and therefore it got a quick refutation from Galileo before he argued the validity of the newly proposed one. Sixthly, the velocity of a freely falling object cannot be directly measured in Galileo's time. Therefore, in order to verify the truth of the hypothesis, Galileo deduces, using mathematical means, verifiable consequences from the hypothesis, and then he designed experiments to check whether the observed result complies with thus predicted consequences. Here, one deduced consequence of the proposed hypothesis is expressed in Theorem 1 and Proposition 1, which says, quote, The time in which any space is traversed by a body starting from rest and uniformly accelerated is equal to the time in which that same space would be traversed by the same body moving at a uniform speed, whose value is 1/2 the highest and final speed reached during the previous uniformly accelerated motion. Quote, here, all major magnitudes, such as the equal time and the length of space, can be measured in an experiment, and therefore if this deduced consequence can be verified by the observation in a designed experiment, the proposed hypothesis would be verified to a certain extent. In general, the scientific methodology proposed by Galileo on the new science of motion is termed by later historians as one of hypothesis deduction, which is featured by mathematical reasoning and experimental observation. So, my students and readers, this is how Galileo discovered his new science, and this is also the method which scientists, in spite of not necessarily agreeing with Galileo's concrete discoveries, have never abandoned in the scientific human endeavor of studying the nature ever since. Are you familiar with this method? To what extent are you still using this method in your own work?